This animated timeline tracks Elon Musk's predicted dates for landing a human on Mars. The target was originally 2024, then it slipped to 2026. Now, the official projection sits at 2029. SpaceX has built a track record of solving problems the aerospace industry previously considered impossible. They routinely land orbital boosters upright on ships and have turned rocket reuse into a standard, profitable business. But establishing routine launches to low Earth orbit represents roughly the first 1% of the energy and complexity required to reach another planet. A crewed Mars mission involves a massive leap in architectural scale. The proposed plan requires a fleet of 6 starships traveling together, 4 carrying cargo and 2 carrying up to 200 passengers. The remaining 99% of the journey relies entirely on 4 unsolved engineering choke points. Failing to clear any single one of them means the mission physically cannot happen. The first choke point is orbital refueling. A Starship cannot launch from Earth carrying enough propellant to reach Mars. It has to top up in low Earth orbit, a process requiring somewhere between 12 to 15 separate tanker flights to supply the necessary fuel. Docking 2 separate vehicles and pumping 100 tons of supercooled propellant between them in microgravity has never been tested at this scale. SpaceX made real progress in 2024 by successfully transferring propellant between tanks inside a single Starship, but moving cryogenic fluids between 2 entirely separate, docked spacecraft requires managing shifting pressures and sloshing liquids without disturbing their precise alignment. Once the fully fueled ships depart on a standard trajectory, the crew faces a punishing transit of 6 to 9 months, completely exposed outside the protective shield of Earth's magnetic field. This source image captures a sudden solar particle event. These eruptions from the sun can deliver a lethal dose of radiation in hours if the crew is unshielded, compounding the constant degradation caused by high-energy galactic cosmic rays. An emergency on the International Space Station means astronauts are just 4 hours from a safe return to Earth. A deep space transit offers total communication isolation and zero possibility of a rescue trajectory. A minor systems failure easily becomes a fatal event. Arriving at the destination introduces the aerodynamic paradox of the Martian atmosphere. The air is just 1% Earth's density, too thin to rely on parachutes to slow down, but dense enough to easily burn up a heavy spacecraft on entry. This scale diagram highlights the extreme leap in mass. The heaviest object humanity has ever successfully landed on Mars is a 1-ton rover. A fully loaded Starship weighs in at roughly 200 tons. Once safely on the surface, the crew faces a strict mass constraint. It is impossible to pack enough fuel on the outbound trip to fly back to Earth. The theoretical solution requires operating a Sabatier reactor on the Martian surface. This autonomous equipment would mine local water ice and extract carbon dioxide from the thin air to synthesize the 1,200 tons of liquid methane and oxygen needed for the return flight. This means an entirely untested, end-to-end robotic industrial plant must land, survive the extreme Martian winter, and flawlessly manufacture the return fuel before the human crew is even allowed to leave Earth. True progress on this checklist is dictated by orbital mechanics. Earth and Mars align to create a viable, energy-efficient launch window exactly once every 26 months. This calendar interface isolates the finite opportunities remaining in this decade. Miss a window, and you wait more than 2 years. The only viable launch windows are 2026, 2028, 2031, and 2033. The upcoming 2026 window will almost certainly carry robotic cargo to test whether a vehicle of this massive scale can survive entry, descent, and landing. Current engineering timelines suggest 2031 is the absolute earliest credible date for a crewed mission, and that specific date relies on a flawless cascade of successful tests for orbital refueling and propellant production in the preceding windows. Actual progress is measured by hardware that flies and tests that validate the math. Watch the 2026 launch window. What actually lands on the surface will tell you exactly where we are on the checklist.